Hi class. In this lecture here, what we want to talk about is limits and infinity. So more specifically, what happens to some function as you investigate as x increases or decreases without bounds. So basically what we're going to be doing here is we're going to be looking at limits like this. So we're going to be looking at the limit as x goes to infinity, so it increases without bound of some function, or the limit as x goes to negative infinity of f of x, so or as the function decreases without bound. And I'm going to show you a ton of examples today and tricks for evaluating these limits. Okay, so the first thing we're going to do is we're going to talk about how you determine limits at infinity. So like what I mean by determine finite, it means it's going to be equal to something so that the limit's going to exist. Then we're going to talk about how you determine the horizontal asymptotes, if any, of the graph of a function. And then we're going to determine infinite limits at infinity. So I'm going to show you like what I mean by that is that the limits don't exist, that they go on or increase or decrease without bound forever. So we'll introduce this topic by looking at a very, very simple function here. Okay, some rational function. So let's consider this function. F of x is equal to 3x squared divided by x squared plus 1. Okay? And so one thing I want to look at is what is the end behavior of this function? So what I mean by that is I want to find out what happens as the limit as x goes to negative infinity of this function. That's how I describe the end behavior to the left. And then I also want to find the limit as x goes to infinity, so as x increases without bound, gets bigger and bigger and bigger, of this same function. All right, so you got to think back, like, one of the first things we looked at was, how do you find a limit? So we use these table of values, and you just plug these numbers in and see what's going on. So like let's just start at 0. All right, if I plug 0 into this, I get 0 over 1. So this is 0. If I plug 1 in, I end up getting 3 over 2, which is 1.5. So I'm just gonna help us out a little here. But like if I plug 10 into this, okay, let me show you in the calculator what you get. Okay, so you get 3 times 10 squared divided by, and then in parentheses, 10 squared plus 1. And look what you get. You get 2.9703. I'll go out 4 decimal places. 2.9703. If you were to do the same thing and you were to plug in 100, you would get 2.9997. So look, as x is increasing, where does it look like? It's going? Right? It looks like it's going towards. It looks like it's going towards 3 here. Same thing on the other side. All right. If you plug in -1, you're going to get 1.5. Same thing with -10, 2.9703. -100, you get 2.9997. So where does it look like as x going towards negative infinity? It also looks like it's going towards 3. And so you can see what's going on here. As x increases or decreases without bound, it looks like it's going towards 3. And if you look at the graph of this, right? So let me plug this function into the graphing calculator. You get 3x squared divided by, and then in parentheses, x squared plus 1. And I look at the graph. Look, you absolutely can see it. As x is increasing without bound, it looks like you're hitting some type of horizontal asymptote. It looks like it's going to be the number 3 here. And so this was one way looking at the graph to see it, and this is another way, with the table to see how you evaluate these limits. All right, and so this is what this section is going to be about. I'm going to show you some tricks of the trade for evaluating all these limits, and we're not going to use these table of values. There's going to be some tricks, some easier ways to do it, and that's what we're going to investigate in this lecture. All right, so here's some just remarks on this. So the statement, the limit as x goes to negative infinity of f of x equals L, or the limit as x goes to infinity of f of x equals L. So the limit exists, it's equal to some number. This means that the limit exists and the limit is equal to L. And you can see here a close-up visual representation of this. All right. So we're going to talk about, cases like this where the limit is finite, it equals some value, and then we'll talk about another case where it might not be and what that means. So just some, what kind of hinting at this in the previous slide, talking about a horizontal asymptote here. So the line y is equal to L is a horizontal asymptote of the graph of the function when you have this. The limit as x goes to negative infinity of f of x exists and it's equal to L. Or on the other side, the limit as x goes to infinity of f of x is equal to L. So you can see here the horizontal asymptote because this limit existed. Okay. Now it's important to note that you can have situations where the limit as x goes to negative infinity might exist, but then the limit as x goes to infinity might not exist. You're still going to have a horizontal asymptote if any one of these exist, if either one of these limits exist. Okay, the main method we're going to use for evaluating these limits, okay, and this one's going to come up a lot, and it goes like this. If r is a positive rational number, so just remember what a rational number is, it's anything of this form, and c is any real number, think of it as a constant then, okay? If you have the limit as x goes to infinity of a constant divided by x raised to any positive number here, okay, any positive rational number, it's going to be equal to 0. And then the limit, it's the same thing, as x goes to negative infinity of c divided by, in this case, x to the r here, but you're going to negative infinity here, all right, it's still going to be equal to 0, okay? And now here's the thing. The second limit is valid only if x raised to the rth power is defined when x is less than 0. So you'll see some cases in the lecture here where we'll restrict it and just say, okay, this only holds when x is positive, and so on. All right, so just remember this, okay? A constant divided by x raised to any power. This is the big one here. The limit as x goes to infinity or limit as x goes to negative infinity is going to be equal to 0. All right. Finally, when we have the exponential, the limit as x goes to negative infinity of e to the x, right? In this case here, what this is saying is if you want to think about it, it's like x raised to the negative infinity power, right? That's just going to be 0, all right? And then the limit as x goes to infinity of e to the negative x, okay? Negative x, you want to get this negative infinity here. So you got to respect the sign. If I plug infinity in for x, quote unquote, it's e to the negative infinity. That is equal to 0. All right, so remember these two. These two are really important for evaluating here, and you'll see in the coming slide. All right, so let's do some examples so you can see this. So let's find each of these limits. Here will be the first one. We'll start pretty straightforward. Let's look at the limit as x goes to infinity of 5 over x squared. Well, look, this right here looks a lot like this rule right here. Okay, the limit as x goes to infinity of c divided by x to the r. That's just equal to 0. Okay. And that's totally okay. Let's try this one. The limit as x goes to infinity of 7 minus 2 over x minus 5 over x squared. Well, look here. The limit as x goes to infinity of 7, that's just still 7, right? The limit of a constant here, okay? It's a horizontal line, right? That's just still 7. And then look, 2 over x as x goes to infinity. Yeah, it's the rule right here. So this is going to be 0, and this is also 0. We just saw that above. So this limit is just 7. Let's try this one. Let's look at the limit as x goes to infinity of 5e to the negative x. Well, look, e to the negative x as x goes to infinity, e to the negative x as x goes to infinity. Boom, that's just 0. So this is just 5 times 0, which is 0. Yeah, great. Now let's try this one. Let's look at the limit as x goes to negative infinity of 7e to the x plus 3 over x. Okay, we'll just follow your rules, right? Limit as x goes to negative infinity of e to the x. Boom, that's 0. So this is 7 times 0. Plus 3 over x as x goes to infinity, the negative infinity, excuse me. That's just 0 by this rule. Well, 7 times 0 is 0, plus 0 gets you 0. Okay. So we're going to follow these rules. These ones are incredibly simple to evaluate and to look at. So let's look at a case now maybe where it doesn't work out nice and neat. All right, so I'm going to go to the next slide here. Let's try to find this one here, okay? Let's look at the limit as x goes to infinity of 3x minus 5 all over x plus 2. If you just direct substitute this in, right, as x goes to infinity just look in the numerator, 3x minus 5, well, if you just plug infinity in, you get 3 times infinity minus 5. Well, that goes to infinity. That increases without bound. Same thing down here. If you plug in infinity for x, you get infinity plus 2, right? That's still infinity. So you get infinity over infinity. All right. This right here is what's called indeterminate form. Okay. And another form of this looks like infinity over infinity, or another common one is 0 over 0. What that means is when you get an expression in that form, it generally means there's something you can do to evaluate it. The limit will exist, okay? And we've actually seen 0 over 0 before, when we were looking in a previous lecture about how to evaluate limits. Okay, so to do something like this, to resolve this problem, what you're going to do is you're going to divide the numerator and denominator by, in this case, what you do is you look at the denominator and you divide by x raised to the highest degree in the denominator. So in this case, it's x. All right, or you do it by x to the n, where n is the highest degree. And this is more to come on this, okay? All right, we'll do this a lot in the coming slides here. All right, so watch what I'm going to do. I'm going to go the limit as x goes to infinity of 3x minus 5 all over x plus 2. So I'm going to divide, okay, numerator and denominator by x, which is the same thing as multiplying by 1 over x. So this becomes the limit as x goes to infinity of 3x minus 5 divided by x plus 2 divided by x. What I'm going to do now, watch as I do this. I'm going to split the terms up here in the numerator and denominator. So this is the limit as x goes to infinity of 3x over x minus 5 over x divided by x over x plus 2 over x. Now watch what happens when I simplify this, right? So this is the limit as x goes to infinity. The x's cancel here. So this is 3 minus 5 over x divided by x over x is 1 plus 2 over x. Now check this out. Now the limit as x goes to infinity of 3 is 3. Limit as x goes to infinity of 5 divided by x. Well, that's just 0. Divided by, limit as x goes to infinity of 1 is just 1. Limit as x goes to infinity of 2 over x. That's 0. So this is just 3 over 1, or 3. So it worked out. It worked out. And maybe suppose you're skeptical, right? You're like, I don't know if I believe that, Matt. Let me show you the graph and let's take a look. Okay. So again, we're going to do 3x minus 5 divided by x plus 2. And if you look at the graph, okay, there is going to be a vertical asymptote, but look, even as I zoom out, it definitely looks like this graph is, boom, it's hitting a horizontal asymptote right there. Like if you keep zooming out, you definitely see it's definitely bumping up against something. So indeed, this is working out. Okay, this method that I'm showing you here. All right, so let's try some more, just so you can see the procedure or how this is done. All right, so let's find each of these limits. We'll start with this one here. Let's look at the limit as x goes to infinity of 4x plus 7 divided by 3x squared plus 2. So here's what you can do. You're going to look down here, okay? And you see that the degree here is 2. So what you're going to do is you're going to divide both the numerator and denominator by x squared. Okay. You can do that because just like up here, you're multiplying by 1 over x divided by 1 over x, which is just 1. So you can multiply anything by 1. So you split it up. This limit as x goes to infinity of 4x over x squared plus 7 over x squared divided by 3x squared over x squared plus 2 over x squared. Clean this up, all right? So this is the limit as x goes to infinity. This becomes 4 over x plus 7 over x squared. X squared cancels, so you're left with 3 plus 2 over x squared. Well, now look what happens. As x goes to infinity, this and this both go to 0. X goes to infinity of 3 is just 3, and this goes to 0. So you're just left with 0 over 3, or 0. That's it. We got it. Piece of cake. Let's try this one. Let's look at the limit as x goes to infinity of 5x squared plus 2 divided by 7x squared plus 3. So again, highest denominator or highest degree in the denominator is 2. So this becomes the limit as x goes to infinity 5x squared plus 2 divided by x squared divided by 7x squared plus 3 divided by x squared. So split it up again. This becomes 5x squared over x squared plus 2 over x squared divided by 7x squared over x squared plus 3 over x squared. And look, you can see what's happening here, right? X squareds are going to cancel. So this is the limit as x goes to infinity of 5 plus 2 over x squared. X squareds are going to cancel here. So this becomes 7 plus 3 over x squared. And look, these two go to 0, right? So this is 5 plus 0 over 7 plus 0. So this limit is 5/7. That's it. Let's try another one here. Let's look at the limit as x goes to infinity. Let's look at x cubed plus 2 all over 3x squared plus 4. All right, well, look, highest degree in the denominator here is 2 again, all right? So this becomes the limit as x goes to infinity. I'm going to divide everything by x squared. Break it up, break it up. So this is the limit as x goes to infinity. This is x cubed over x squared plus 2 over x squared divided by 3x squared over x squared plus 4 over x squared. Well, look, clean it up, clean it up. This is the limit as x goes to infinity. X cubed divided by x squared just gets me x plus 2 over x squared divided by, this becomes 3 plus 4 over x squared. Now look, plug in infinity. Well, as x goes to infinity, x goes to infinity. Plus 0 divided by 3 plus 0. Well, infinity divided by 3 is still infinity. So this increases without bound. I just want to be clear that when you say a limit equals infinity, that still means it does not exist. Okay, it's just telling you that it's describing the behavior. Okay, it's saying, look, you're going all the way to infinity. You're increasing without bound. Okay. Let's talk about a way you can evaluate these limits actually without this trick. Okay. So this is a guideline for finding limits at plus or minus infinity of these rational functions. So look, these are all rational functions. And it goes like this. If the degree of the numerator is less than the degree of the denominator, okay, then the limit of the rational function is 0. So this is a case when you have something like x to the m divided by x to the n. And this is where m is less than n. Okay, so the degree of the numerator is less than this. So it would be something like this. Like x squared over x cubed. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. Okay, so it'll be something like this. X to the m divided by x to the n, where m is equal to n. So like x to the 5th divided by x to the 5th. All right, the degrees are the same. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. It increases or decreases without bound. So this is x to the m divided by x to the m, and this is where m is greater than n. So something like x to the 7th divided by x cubed. It's just gonna go to positive or negative infinity. So you can just very easily look, like if you look here, the degree of the denominator is greater, right? The degree up here is 1, here it's 2, gets 0. The degrees are the same. Then the limit is the ratio of the leading coefficients, which is 5 over 7. Look at that. Down here, the degree of the numerator is higher than the degree of the denominator. The limit does not exist. All right, let's put these, another round of examples just so you can see it. All right, so again, let's find each limit. Let's look at the limit as x goes to infinity of 2x minus 1 over 4x squared plus 1. Well, look here. The degree of the numerator is less than the degree of the denominator. So this is just going to be equal to 0. That's it. You can just very, very easily look at it and say, okay, this is option number 1 on previous slide. B here. Now this is the limit as x goes to infinity. Let's look at 10x squared plus 1 divided by 12x squared plus 5. Well, look here. Do you notice degree is 2? Degree is 2. So this limit here is just going to be the ratio of the leading coefficients, which is 10 and 12, which reduces to 5/6. And this is just from option number 2 because the degrees are equal. Now let's try this one. This one's really interesting actually. Okay, let's look at the limit as x goes to negative infinity of 5 times x to the 5th power plus 1 divided by 2x cubed plus 3. All right, so you notice here that the degree of the numerator is larger than the degree of the denominator, right? And now you always have to respect this sign, and this is why it's so important. A lot of times people think, oh, you know, you're going to negative infinity, so this is going to go to negative infinity as well. But look, if you have the 5th power, all right, and you take a negative number to the 5th power, you get a negative. If you take a negative number and you cube it, you get a negative. So you get a negative divided by a negative. So you have to be careful. This is going to go to positive infinity, okay? And this is because the degree is larger in the numerator than the denominator. And this is from option number 3 on previous slide. Okay, let me show you this in the calculator. You know, just so you can see it, right? So you have 5x raised to the 5th power plus 1 divided by, and then in parentheses, 2x to the 3rd power plus 3. And if you graph this, this is where it gets tricky here. Do you see this little blue part up here? You're going to want to zoom out. And look, you can see that this graph is going up really, really quickly as x goes to the left. So as x goes to negative infinity, yeah, this graph is shooting up really, really quickly over here. So this holds. All right, let me look at a rather interesting one, okay? So this is an example where a graph has 2 different horizontal asymptotes, okay? So let's consider this function. Let's consider f of x is equal to 1 over 1 plus e to the negative x, okay? Let's look at this. Let's look at the limit as x goes to infinity of 1 over 1 plus e to the negative x. Well, look here, you know, as x goes to infinity, what is e to the negative x? Let's go back. Okay, as x goes to infinity of e to the negative x, it's 0. So this is 1 over 1 plus 0, which is just 1. But now notice this is really cool. Notice what happens. Limit as x goes to negative infinity of 1 over 1 plus e to the negative x. Well, if you plug in negative infinity in here, you get negative is a positive. Well, e to the infinity is a really large number, right? It's just increasing without bounds. So if you take 1 and divide it by a really large number, right, this function is going to 0, okay? So this is crazy. It has this function has 2 different horizontal asymptotes. So like what you're going to notice when I'm going to show you the graph in the graphing calculator. Here's one. This graph is going to look really, really, really cool. It's gonna like look like this, okay? Watch what happens. Let me show you. So this is 1 divided by, and then in parentheses, 1 plus e to the negative x. And you got to zoom in here. And you can see exactly what I'm talking about here. Whoop, just like that. It's pretty wild here that it has these two different horizontal asymptotes, and that's okay, and that's totally okay. All right, let's talk about some trig limits now. Okay. Let's look at this one. Let's look at the limit as x goes to infinity of sine of x. Well, if you think of the sine graph, right? The sine graph is just going to go like this, right? It's just going to oscillate forever. Okay? So when you have a graph that oscillates between two numbers, okay? And as x is increasing without bound, as x gets larger and larger, it's still going to oscillate. This limit does not exist, okay? And this is because sine of x oscillates between -1 and 1. Okay, so oscillating, we even saw this in previous lectures, right? Oscillating between two values means the limit does not exist. But now let's check out this one, okay? Let's look at the limit as x goes to infinity of sine of x over x. Well, how are we going to even start this? So it's a really interesting problem. You start by doing this. Just look at sine, okay? So this is how we start this one. We know sine is bounded between -1 and 1. Now, we're looking as x increases without bounds. So for x greater than 0, okay, the following holds. If you were to divide everything by x, you would still have the same equality, as long as x is a positive number, right? Because then you're going to flip the inequalities if you divide by a negative. So what I'm going to do now, let me take the limit as x goes to infinity of everything. Well, what's this limit? As x goes to infinity of -1 over x, it's 0. As x goes to infinity of 1 over x, it's 0. So this is 0 is less than or equal to the limit of sine of x over x, which is less than or equal to 0. So by the squeeze theorem, we see that this limit as x goes to infinity of sine of x over x, that's indeed equal to 0 here. All right, so we got some problems here. Got some methods. Let's work some more interesting ones. Okay, so some problems that I haven't covered that you'll get to just see some more tricky examples. So I've got three more slides of just some problems that are a little bit more difficult and just applications of what we've been talking about here. Okay. All right, so let's look at some limits at infinity that we haven't seen before here. So let's start with this one. Let's look at the limit as x goes to infinity of 5x to the 3/2 divided by 4x plus 1. All right, well, you notice right off the bat, like we haven't done anything with where an exponent is a rational number. It's always been an integer, or a positive integer, actually. So it doesn't matter. You're still going to solve this the same way. Okay, let me divide by x here. Okay, so everything by x. So this is the limit as x goes to infinity of 5x to the 3/2 divided by x all over 4x plus 1 divided by x. So this here is going to be equal to the limit. I'm just going to clean it up, right? 3/2 divided by x, this just ends up being x to the 1/2 power. All over, this ends up just being 4 plus 1 over x. I hope you can see that here. Well, look, as x goes to infinity, okay, x to the 1/2 power goes to infinity, and this goes to 0. So this is 5 times infinity over 4 plus 0. Yeah, so this one goes to infinity, so it does not exist. And look, the exponent, the highest exponent here is greater than the highest exponent in the denominator, so it's the same procedure. It's just going to DNA, it does not exist. Let's try this one. Limit as x goes to infinity of, let's look at 5x, I'll switch it up. 5x divided by 4x to the 3/2 plus 1. Well, look, you could divide everything by x to the 3/2, and when you do, what you'll see is you're just going to get 5 divided by x to the 1/2 here. But you could just use that procedure I've been talking about. The value here is 1. The value down here is 3/2 for the highest exponent. The denominator dominates, so this limit is equal to 0. All right, let's try this last one. It's because it's very interesting, a little bit trickier. Limit as x goes to infinity of 5 minus 2x to the 5/2 power divided by 3x squared minus 4. Okay, so for this one here, it's really interesting, right? So you're going to say, okay, well, look, the exponent is higher in the numerator, right? So that means this goes to infinity. But you have to respect the sign of the coefficient here, okay? So it's going to go to positive infinity, but you're going to still be multiplying it by a negative number here. Okay, still going to be multiplying it by this negative number. So respect the sign. So it's going to be dominated by a -2. So a negative times infinity is going to get you going to negative infinity. Okay. Let's take a look at stuff involving some square roots now. Okay. So let's try this one. Let's look at the limit as x goes to infinity of x divided by the square root of x squared minus x. Well, look, what's confusing is you have the square root, right? So what's the highest exponent here? It's the squared, but you're still square rooting it, okay? So you're just going to multiply by the square root of x squared here in the denominator, excuse me, times 1 over the square root of x squared. Sorry about that. Well, what is the square root of x squared? It's just x. So now watch what happens when I distribute this through. So this is the limit as x goes to infinity. X times 1 over x is x over x divided by. This is the square root of x squared minus x divided by the square root of x squared. So this is just x squared minus x divided by x squared square rooted. So limit as x goes to infinity here. This is 1 over here. Watch what's going to happen. Okay, square root of x squared over x squared is 1 minus x over x squared is 1 over x. Well, limit as x goes to infinity. This right here is 0, so this is 1 over the square root of 1 minus 0 which is 1 over 1. This limit is equal to 1. All right, I want to show you a trick now to do this without all this extra jargon in it. All this extra work, just like intuitively, okay? So let's look at the limit as x goes to infinity of the square root of x to the 4th minus 1 all over x cubed minus 1. Look here, if you square root x squared, you get x, right? So then it would be 1 and 1. So they have the same degree, so you got the ratio of the leading coefficients. If you look here, right? If you look here, okay, just look at something like this, x to the 4th over x, square root of x to the 4th over x cubed. These, as x gets sufficiently large, this minus 1 and minus 1 doesn't matter. Well, look, this simplifies to x squared over x cubed. So the degree of the denominator is larger. So this is just going to be 0 by that law. And you could go through, all right? Another way you could solve this you could take this and you could go through with the procedure that we talked about and multiply it by 1 over x cubed, which is the same thing as the square root of x to the 6th. That's how you could combine it. And then you'll still get the same answer. All right, let's end talking about just some trig ones, some interesting ones. Okay, so these will be our last ones here. Let's look at the limit as x goes to infinity of cosine of 1 over x. Well, how are you going to tackle this? You're going to say, okay, as x goes to infinity, what does 1 over x go to? It goes to 0. So this is just cosine of 0, which is 1. Let's look at this one. Limit as x goes to infinity of sine of 2x over x. Well, that looks a lot like sine of x over x. So if you just put a 2 in here, go 2 sine of 2x, all divided by 2x. Notice how it's the same thing here, inside the sine and what's in the denominator. Well, we know that this goes to 0 then. So this is just 2 times 0, which is 0. Let's try this one. Limit as x goes to infinity of x minus cosine of x all over x. So this is really weird. So what I'm going to do is I'm going to break it up into two parts. So it's the limit as x goes to infinity of x over x minus cosine of x over x, which is the limit as x goes to infinity of 1 minus cosine of x over x. Well, look, the limit as x goes to infinity of 1 is just 1. And what's really cool is this cosine of x over x is the same thing. So you would solve it the same way as we did sine of x over x. And this just goes to 0. So this limit's 1. All right, let's end on this last one, something really cool. Let's look at the limit as x goes to infinity of the natural log of 1 plus e to the negative x. So it looks daunting, but look, limit as x goes to infinity of e to the negative x. Well, that's just 0 by our rules. So this just evaluates as the natural log of 1 plus 0, which is the natural log of 1, which we know is just 0. All right, class, a lot of examples in here. You're going to get a chance to always practice this on your homework. And, as always, if you have any questions, please let me know.